Good morning. We are going to discuss what electrode potential means and how quantum capacitance is related to this. So, to begin with, the first question is what is an electrode? So, an electrode is an electronic conductor immersed in an electrolyte of ionic conductor. So, it's both some sort of an electronic conductor, it could be a metal or an insulator plus ionic conductor. So this is usually the solid part, and these ionic conductors, if we are considering liquid electrolytes, this is usually the liquid part, right? So the function of an electrode is to provide electric current. So the electrode doesn't work in isolation. That is, this solid is not working in isolation, and the term electrode is often used to refer to both the electronic conductor and the ionic electrolyte together. So now let's understand the difference between different types of electrodes. We have polarizable and non-polarizable electrodes. The thing to note here is that polarizability in electrochemistry is different from polarization in physics. So in physics, we often use the term polarization to indicate dipole polarization. But here we in electrochemistry, when we mean polarization, it means deviation of electrode potential. So it is not dipole polarization in electrochemistry. So that's something that we need to be very aware of. So we're defining polarization as deviation in electrode potential, but we don't yet know what electrode potential really means, and we're going to figure that out. And to figure that out, we are dividing these electrodes into two types, polarizable and non-polarizable. Essentially, non-polarizable is where charge transfer happens. So in non-polarizable electrode, charge transfer happens, and here there is no charge transfer. So polarizable electrodes are those that have no charge transfer. That means no electrons or ions. Whereas non-polarizable electrodes, there is a charge transfer. So this could be of two types. One is electrons transferred or ions. For example, you could have a redox reaction that would be, Fe aqueous 2 plus becomes, Fe3 plus aqueous and gives out an electron that will go through the conductor. So an electron is being transferred across the electrolyte into the electronic conductor. So that's what is a charge transfer of an electron means. Charge transfer of ion, a simple way to understand this is if you are to take just simple, an iron, metal or zinc, let's say just iron, and you place it in some electrolyte, right? Even without anything, these ions are going to leach out from the metal and go into the aqueous solution. So Fe2 plus, which was in metal, would become Fe2 plus aqueous. I'm using aqueous, but it could be non-aqueous electrolyte too. It is essentially what we are saying is that it is going from the metal into the electrolyte. So an ion from the metal is being transferred into the electrolyte. So that is an ion transfer. Whereas an electron transfer is the ion is still in the electrolyte. It just changed the redox state, and an electron goes through the conductor. So for polarizable electrodes, there is no charge transfer. This means there is electrostatic equilibrium. So we will see what this electrostatic equilibrium means in a minute. We'll come back to that. Whereas in case of non-polarizable, we have charge transfer, right? So here we have charge transfer equilibrium. So what we are going to do now is to understand the electrode potential. We're first going to understand what electrostatic equilibrium means. To do this, we'll have to revise some concepts very quickly from electrostatics, and then we'll come back again to, after revising the electrostatic concepts, we'll come back to the polarizable electrode, and then we'll look at the what charge transfer equilibrium means. And after considering all these, we will derive an expression for what electrode potential is and how quantum capacitance would play a role in this electrode potential, and how it is relevant for electrodes like SPAN, for example, or PPS, or any other sulfur electrode. So let's do the revision of electrostatic equilibrium. Right. So to revise electrostatic equilibrium, first, we need to ask ourselves, about what charge, what electric field, and what potential mean. So charge is a property of a massive body, and this charge can cause electric field in the space. So if I have a charged body here, right, it can cause electric field around it in the space. So the electric field and potential themselves exist in space. They're a property of the space. Space is not just nothingness, it is something. That's why it bends around Earth, for example, because of gravity. So that space is not nothingness, it is something. So it is the space that is affected by the charge, and the E field is a property of the space, and so is the potential. Potential is essentially, this is again electrostatic potential. So in electrostatic potential is essentially a further specification of the electric field. The way we define E field is negative of grad phi, where phi is the electrostatic potential. So if you have a conductor, inside a conductor, the total electric field is 0, right? Total E is equal to 0 inside a conductor. So this is a conductor, and then phi would be constant. So now what we are going to look at is how we can treat entire electrostatics essentially as a boundary value problem. So we have in electrostatics, there is no motion of charges. So curl E is equal to 0. There is no microscopic curling of E. And we know from Gauss's law that del dot E is equal to rho by epsilon naught, and E is equal to negative grad phi. So if I plug this in here, what we would get is divergence of negative gradient is equal to rho by epsilon naught, or Laplacian of phi is equal to minus rho by epsilon naught. This is the Laplace's equation. So the entire solution for electrostatic problems could be figured out by solving this equation. If you know the charge, you put in the charge, and you basically figure out a way to solve this equation, right? So for solving this problem, we also have to apply boundary conditions, because this is a differential equation. What we mean by that, so let's look at a physical picture. A physical picture is, for example, if I have some metal or some conductor here. So I have a conductor here. This is not an infinite conductor. This is a finite conductor. And because it is a finite conductor, really you still have, although you have no net charge, you have surface dipoles, because the bonds at the edge are cut off, right? So you have a surface dipole. Inside the conductor, phi is inside. This is constant inside the conductor because there is no electric field inside the conductor. So now what would happen if I were to bring some charge here, some charge Q, right? So this charge Q would in turn induce some charge here, right? On the surface, it would disturb this dipole, so it would induce the charge here. And inside the conductor, there is no net charge. All the charge is on the surface in a conductor. So because inside there is no net charge, the Laplace's equation is del square phi is equal to 0, which becomes Poisson's equation. And outside we have a potential that, or an electric field that we are supplying using a charge Q. So let's suppose that the potential here is psi out, and let's say the surface is chi surface. So if you're going from inside the conductor, if you're going out, the electric field itself should be a constant function, right? And this can be proved very easily using Gauss's law. The electric field itself should be constant. There should be no discontinuities, right? And that's what we use the boundary conditions for, that to make sure that the electric field is continuous as you go from inside the conductor to outside the conductor. So because the electric field is continuous, what this means then is that phi inside is equal to essentially psi out plus chi surface, right? Or I can write psi out as phi inside minus chi surface. So this again, once again, note that the surface is coming from, the surface potential is coming from dipole contributions. It is not just charge. There is a difference between having net charge and dipole. The total charge is still 0 in the metal because you have the same number of nuclei and the same number of electrons, and so the total charge is 0. But because the charges are in a particular configuration, there is a non-zero dipole moment, although the net charge is 0. That's where we are getting this surface potential from, right? So that's what one has to bear in mind while studying electrochemistry problems, that electric fields can still come from neutral solids because they have dipole contributions, right? So if total charge is equal to 0, doesn't mean that the potential is 0. So now let's ask ourselves what would happen if I were to put two metal pieces together, right? So let's call this A, let's call this B. So what we're trying to look at again is we're trying to look at polarizable electrodes, because our goal is to define what electrode potential means. And what we have seen is that electrostatics is a boundary value problem, and we have seen that psi out is equal to phi in minus chi surface. Now we're trying to put two metal pieces together, piece A and piece B of different metals. Let's say to make this more general, let's say that this metal is not necessarily neutral. Let's say it has a charge of sigma prime A. So if you want to study neutral metal pieces, that means you just equate the sigma A prime is equal to 0 essentially in the equation. And this, let's say, has sigma B prime, right? And let's say this has dipole of A and dipole of B on the surface. So when we are saying net charge, this is the total charge and total dipole. What we are trying to say is that in general, the electric potential phi is equal to rho of r prime d cube r prime by, so this is a function of r, is r minus r prime. That means if I have some charge distribution here, and I would like to find out what the potential is at some point P due to this charge distribution. From the origin, the distance to this point is R. So I can divide, I can think of this whatever charge distribution, I can cut it into very small pieces, right? And I have a vector that goes from the origin to each cell in this charge distribution, and I label this as R prime. Then I go to this one, I'm cutting these into small tiny pieces so I can consider each tiny piece as a point charge, and then find out what is the potential due to this point charge at point P. So that would be, within this volume, the charge is this much, right? Charge density times the volume, the tiny volume, and the distance between this point and point P is essentially the difference between R and R prime. So this would be R minus R prime. So that's what we have as the potential, right? So this potential, if you look at the function f of r prime or f of r as 1 over r minus r prime, if you take just this function, we can expand it in a Taylor series. We can expand it in a Taylor series around r prime is equal to 0. That is, we can expand it around the origin. So if we expand it around the origin, so f of r prime would be equal to f of r prime at r prime is equal to 0, right? Plus sigma I is equal to 1 to 3, 1 to 3 because you have x, y, and z. Ri prime to f by dou ri prime at r prime is equal to 0, plus so on and so forth. Right? That's the Taylor expansion. So if you actually perform the Taylor expansion on this function, you will see that the first term is what we call as the monopole term, and the second term is what we call as the dipole term. So the monopole term could be 0. That is, if I have, for example, if I have just an atom, I have a positive charge and a negative charge, right? So if I am very, very far from this atom somewhere here at point P, it appears to me like there is no net charge because the electron and the proton are so close together that the total charge appears to be 0. So the monopole term appears to be 0. Yet there would be a non-zero potential because the electron and proton are not on top of each other. There is some gap between them. So there is a dipole contribution, that is the first term, right? So here when we are saying sigma A prime, we mean that gives rise to a monopole term. That is, there is total charge. So if you are at point P here, you see a net charge, net total charge, right? And even if you don't have the net total charge, like in case of an atom, you can still see the effect of a dipole because you have a positive charge separated from a negative charge. And that's what we are representing here as a dipole of A and dipole of B. So now when we put these two things together, right? So originally we have sigma prime A, and around the surface we have the dipole term for A, and we have sigma B prime, that is the net charge on B, and we have dipole for B, right? And the inner potential for A is phi A prime, let's say, and the outer potential for A is psi A prime, and then same thing here, phi B prime and psi B prime. So now if they contact each other, recall we are studying polarizable electrode. That means there is no charge transfer across the interface, right? So there is no charge transfer across the interface. You get whatever is at the interface, right? And then here you have now the potential changes from phi A prime to phi A, and here it changes from phi B prime to phi B, and here it becomes psi A, it becomes psi B outside, right? So if we want to look at what is the difference between phi A and phi B, phi A minus phi B, we can call this as delta phi A by B. There is a difference, interfacial difference between phi A and phi B. this would have some potential, right, coming from the total charge at the interface. So there is no charge transfer. So whatever the sigma A prime and sigma B prime, they mixed up here at the interface, they give you some new charge sigma at the interface, right? That's what we are calling here, that this new charge plus potential due to dipole term at A slash B interface. Recall that by Taylor expansion we can do monopole term plus dipole term, and that's what we are doing. So essentially what we are saying is that when we join two pieces A and B, it's not just that the total charge would add up, but it is also the orientation of the charges would be different. It would not just be a sum of the two charges. There is no charge transfer, yet the way the charges would rearrange, the distribution of charges is not simply an arithmetic sum of the total charges. So the sigma at A by B is not equal to sigma A prime plus sigma B prime, right? Similarly, the dipole at A by B is not equal to dipole at A plus dipole at B, because when the charges come in together, depending upon what kind of charges they are, right, they would rearrange in such a way that the distribution would be in such a way at the interface, right, that this is not in general a valid assumption, right? Now we have seen that psi is equal to phi minus chi, where chi is the surface potential, right? Then we can write delta psi of AB, that is the difference between the outer potential. This is the difference between inner potential. That would be equal to phi A minus chi A minus phi B minus chi B. So that would be equal to phi A minus phi B minus chi A minus chi B. Or that would be equal to delta phi A slash B minus delta chi A slash B, right? Or in other words, what we get is delta psi of A by B is equal to delta phi A by B minus delta chi A by B. So here what you have to note is that these two terms don't cancel out, because when you put two surfaces together, the distribution of charges would not just be an arithmetic sum, right? That's why these two don't cancel out, right? The surface contributions don't cancel out, because when two dipoles mix, you get a new dipole that is not the arithmetic sum. So here, if I redraw the diagram, so here I have metal A and metal B, and whatever we are looking at, this inside potential difference is delta phi A by B. So this is the inner or interfacial potential difference. This depends upon how charges redistribute at the interface, how the dipoles redistribute at the interface. Whereas this delta chi of A, psi of AB, that would be, this is psi A and this is psi B outside. So the difference between this would be delta psi AB. So this is the outer potential difference. So what we can measure is the outer potential. Outer can be measured. The inner potential cannot be measured. The reason is, let's say we want to measure the inner potential. How would we go about it? We would go about it, let's say, with some probe, some sort of a probe, some sort of a probe that's going to measure this. But if you put the probe, because of the presence of the probe, you change the distribution of electrons here. So, and because you change the distribution, then you're not really probing the inner potential difference. So in electrochemistry, what we are measuring in polarizable electrodes is this outer potential, or delta psi of A by B. In general, this inner potential difference is called Galvani potential difference, and the outer potential difference is called Volta potential difference. Right? So if you put two polarizable electrodes where there is no charge transfer, then the outer potential difference is equal to the inner potential difference minus a slight term that comes because the dipoles or the charges have rearranged on the surface. Right? They're not just the arithmetic sum. They're different because they redistribute according to what kind of charges are there and how the charges are distributed. So this would depend upon the crystal structure of the metals or the elemental composition of the metals, right? So that's why we are deducting this to account for the redistribution, right? This is for polarizable electrodes. Recall that for polarizable electrodes, there is no charge transfer, so the electrons are not flowing this way or that way. Everything, all the charge is at the interface. There is no charge flowing into either A or B. So we have an electrostatic equilibrium and we have two polarizable electrodes. Now, let's now go about talking about charge transfer equilibrium. That is, we would like to talk about non-polarizable electrodes. So in case of non-polarizable electrodes, there is either electron transfer or ion transfer. So to do this, we have to take a step back and look at a little bit of thermodynamics very quickly. So if you have any system, you have a number of electrons, for example, in the metal, or if you have the electrolyte, you have a number of ions. So it's not a single particle system. You have multiple particles, right? So usually you have a system of n particles, right? And your system has a volume V and energy E, and there is entropy. S is the entropy. And in general, any system of particles, so if you have a system of particles, n particles, right? So n particles, and we have a volume V and the total energy is E, then I can define a function entropy which depends upon E, V, and N. And from thermodynamics, we know that you want to maximize this entropy, or basically you set ds is equal to 0 whenever you want to see where the system would equilibrate, right? So if we can write as a function of EVN, entropy is a function of EVN. We can also write energy as function of entropy, volume, and number. Or I can write a little change in energy, dE would be essentially dou E by dou S, right, at constant volume and number, ds plus dou E by dou V at constant entropy and number, dV plus dou E by dou N at constant entropy and volume, dN, right? So this would be the temperature, ds, this would be the negative of pressure, dV, and this, for a metal or for a semiconductor, this is essentially the Fermi level, or here we're going to talk about it as chemical potential. So one thing we have to note here is that when we are using the term chemical potential and Fermi level, one has to be very careful about this definition of chemical potential, because the chemical potential that is used in physics and the electrochemical potential, sometimes there is a subtle difference. So here we're going to just write this as mu prime, just to make sure that we are defining this mu as a chemical potential of the system like we do in statistical mechanics, right? So that would be mu prime dN, right? And this is equal to dE. So then I can recast this equation, right, to write what ds is, because to see where the system equilibrates, right, we need to set ds is equal to 0. And we are looking at a thermodynamic perspective because in case of non-polarizable electrodes, there is charge transfer. That means there is a flow of particles from one side of the system, say the electrolyte, into the metal, or the other way around, whichever way, right? So there is a flow of particles. So it's going to equilibrate somewhere, and that's what we want to find out, where it equilibrates. So to find that, we're setting ds is equal to 0. So to do that, from here, we can find out what ds is. Then basically ds would be dE by t, right? Plus P by T dV minus mu prime by T dN, right? Or I can write dou S by dou N as minus mu prime by T, correct? So now let's say if I have two systems, this has some energy, some volume, some N. So let's just say E1, N1, N2, and here I have E2, V2, N2, and I have some sort of a barrier in between, right? And now I suddenly remove this barrier, or I make this barrier permeable to particles to pass through, and we want to see where the system would equilibrate. So this, if it has an entropy of S1, and if this has an entropy of S2, then the total entropy is S1 plus S2. We are going to ignore the interaction term here, because the interaction term itself is very little, because now the charges are able to move across. So that means ds is equal to ds1 plus ds2, right? So that means this is dou s by dou n1 dn1 plus dou s2 by dou n2 dn2. So what we are saying here is that essentially only particles are going across, right? The particles from one side of the from box 1 are going to box 2, or box 2 are going to box 1, right? And so the total particles don't change, because total particles is n1 plus n2. So the total number dn is equal to 0. They may go from box 1 to box 2, or box 2 to box 1, but the total particles remains constant. That means dn1 plus dn2 is equal to 0, or dn1 is equal to minus dn2. That is, if one particle has gone from box 1 to box 2, that means you reduce, here you would get n1 minus 1, and here you would get n2 plus 1, right? So that's why you have a negative sign. So we could plug that in here. Then I would have dou S1 by dou N1 dN1 minus dou S2 by dou N2 dN1. Instead of this plus, we put in minus. Instead of dN2, we put in dN1 because of this. So now if you pull out dN1 as common, you would have dou S1 minus dou N1 dou S2 by dou N2 dN1. And our goal is to equilibrate this, so we set this to 0. And if we set this to 0, essentially we want dou S1 by dou N1 to be equal to dou S2 by dou N2 for equilibrium. And if I go back, you can see that dou S by dou N is related to the Fermi level, right? So minus mu prime by T. So that means minus mu1 prime by T should be equal to minus mu2 prime by T, or that implies mu1 prime should become mu2 prime. So when mu1 prime becomes equal to mu2 prime, these two systems would equilibrate. In case of what we are looking at, we are trying to look at if we put two things together and we are allowing particles to go from one side to another side, that is, there is charge transfer, then the equilibrium is reached when the Fermi levels are equal. That's what this is saying, that when Fermi levels become equal, an equilibrium is reached, right? So equipped with that, now let's go back to our example of non-polarizable electrodes. In case of polarizable electrodes, we have seen that if I put A and B together, in case of polarizable, we saw that the outer potential difference, delta psi AB, is equal to the inner potential difference, delta phi AB, minus whatever is the redistribution of the dipoles. Now we are doing the same thing for non-polarizable. However, in case of non-polarizable electrodes, now you have transfer of electrons or ions. So we're going to first look at just transfer of ions, and then you can extend it to transfer of ions very easily if you want. So if there is transfer, now the quantum mechanical features become important. When we are looking at polarizable electrodes, we really did not need to invoke any quantum mechanics. All that we did was electrostatics, really. right? We considered this metal as a lump of conductor. We didn't go through any quantum effects because there is no motion of charges, so everything is static. So we didn't need any quantum effects there. But once there is a non-polarizable electrode, charge is going from one place to another place, and as we have seen on the previous slide, this would mean that the Fermi level of A should become the Fermi level of B. This is what we had seen as mu1 prime becomes equal to mu2 prime. Recall that I put a prime because electrochemical potential is a little different, and so we don't want to get confused between the Fermi level and the chemical potential really. And I'll make what that difference is. I'll make that difference clear in a moment. So now if you look at the structure of metal A, you have a Fermi level. So let's call this Fermi level of A. Right below this, all the electrons are filled, all the electronic states are filled, and there is a vacuum, right? And the vacuum state, the potential at the vacuum state is minus E psi A. That is the potential outside, right? So if you want to take an electron from the Fermi level, right, all the way to here to the vacuum, then this essentially is your work function. We're going to call that as alpha E of A. But if you go to the surface, right, this only goes up till the surface. The inner potential ends at the surface, and there is a difference between the surface and the vacuum state, and that difference comes because there is this the metal or the part A, it ends abruptly, right? So if I have a metal piece A, it ends abruptly at the surface. So you have the dipole term at the surface, like I talked about before, right? So if you're going from inside to vacuum level, you go from the Fermi level all the way to the surface here, and this is the surface, and then from surface you go to vacuum level, right? So this is minus E chi of A. That is the surface. You would have similar things for B. So I'm going to draw B with green color now. So so if I draw B with green color, let me draw the Fermi level a little higher so that there is difference between these two. So for B, you have the same things, and essentially you would have minus E psi B minus E phi B, and this would be minus E chi B, and this would be the work function of B, right? And the difference between Fermi level and the chemical potential mu is essentially here. This is what we write as mu E of A. So mu E of A is the difference between the Fermi level and the surface, not the vacuum, right? And the work function is the difference between Fermi level and the vacuum level. So similarly, in case of B, the difference between Fermi level and the surface, right? This is the surface. This extra term is coming from the surface dipole on A or B. So this would be mu E of B. So now, as we have seen in case of thermodynamic equilibrium, if we put these two together, if we put A and B together, then charges are going to go across. And the way they would go across is they would go from higher Fermi level to a lower Fermi level, and they would equilibrate that way. So once they have equilibrated, you would get the two Fermi levels basically would equalize once you put them in contact. So if you look at EF of A here, right? This is EF of A, and this is minus E psi of A. So that would be equal to mu E of A minus E phi A. Or another way to write it is, let me write it this way, so that it's easier to grasp. So here, let's say this value is x and this value is y. So if we want to find the gap, we just do x minus y. Doesn't matter which way you go. You could do y minus x as well. Essentially, whatever you choose, x minus y or y minus x, we have to do the same thing all throughout. So essentially, mu e of a would be, x minus y. So that would be equal to ef of a minus e phi a, or that would be equal to ef of a plus e phi b. E phi a. Similarly, mu e of b would be equal to ef of b plus e phi of b, right? And we know that EFA becomes EFB, right? So from here, I can write EF of A as mu E of A minus E phi A, and EF of B as mu E B minus E phi B, right? And these two become equal when they're equilibrating. So these two become equal. So then we would have mu E of A minus E phi A is equal to mu EB minus E phi B. Or then I can write E times phi A minus phi B is equal to mu E of A minus mu E of B. Or I can write delta phi A by B is mu E of A minus mu E of B by E. That would be the inner potential difference when they reach charge transfer equilibrium. Once again, draw this diagram by yourself. Mu E would be the difference between the Fermi level and the surface potential, right? And the surface, from the surface to vacuum, you have this extra term. From the vacuum to the Fermi level is the work function, right? So you may want to draw this diagram yourself to understand what these different terms mean, right? Now similarly, we can write alpha, right? Alpha is the distance between the Fermi level and the vacuum, right? So then I can write alpha E of A as EF of A plus E psi of A, right? So here we have negative E psi A, negative E phi A. This is the surface. This gap is negative E chi A, and this is mu E of A, and this is the Fermi level EF of A, and this between the vacuum level and Fermi level is alpha E of A. So this alpha E of A, the difference between EF and this, so EF minus this, so you get EF plus E psi A. Similarly, alpha EB, you could draw the same diagram for alpha EB and you would get EFB plus E psi B. But we know that when we put A and B together, the Fermi levels are equal, or in other words, alpha EA minus E psi A is equal to alpha EB minus E psi B, right? Or we could write psi A minus psi B as alpha E A minus alpha E B by E. So this is work function of A, and this is work function of B. So the outer potential difference, delta psi of A by B, in case of a polarizable electrodes where charges are allowed to go from one metal to another metal, or one from A to B or B to A, the outer potential difference is determined by the difference in the work functions of the systems, whereas the inner potential is related to the chemical potential itself. So that's the difference one has to make. So now let us look at a an electrode immersed in an electrolyte. So we have say some electrolyte, and then we have an electrode that is immersed in that. This is the metal, this is the solution S. So now the outside potential is psi S, right? So now if we were to draw the energy levels, so we have the psi S, that is a vacuum level, and this is the Fermi level of the electrolyte, that is indicated by S, right? And this is the surface. This is the surface of the electrolyte itself, so that we have here. This is the surface of the electrolyte. So this is going to be minus E chi surface of the solvent with respect to vacuum, right? So S slash V so S slash V is solvent vacuum, and this is minus E psi S, that's the vacuum level, and this is obviously the chemical potential of the solvent itself, right? So now let's draw the metal energy levels in another color here. So the metal Fermi level is below that of the solvent. So this is going to be EF of metal. So we are going to look at an electron going from the solution into the metal, and then you have the surface of the metal. This would be the surface of the metal, right? So that would be somewhere here, let's say. So this would be minus E chi metal and vacuum, and this would be the chemical potential of the metal. So this would be minus E phi of S. This would be minus E phi of M. And then we can look at then the total electrode potential. The total electrode potential would be, if I were to extend the Fermi level of the metal, this would be the total electrode potential would depend upon the real work function of this metal electrode solution interface together. So we call this alpha of electrons, metal and the solvent in vacuum together, right? So if we want to look at just that of the metal, the work function of the metal, that would be this. The metal if we want to look at the work function of the solution, that would be this. So this would be alpha E of S by V, right? And now let's look at the difference between these two things, right? That is EFS and EFM, the difference. That is what we're going to call it as alpha E M by S. This is the difference between the Fermi energy of the solvent and the Fermi energy of the metal. So to find out the net electrode potential, what we need to find out is, how much energy you need to take an electron from the metal and take it from here through the solution into that vacuum state. That's what we're interested in finding out. So to find that out, you can see that we could write that as, if I extend this line, and if I extend the green line, this difference is what we derived as the inner potential, because this is the surface potential of the solvent, and this is the surface potential of the metal. So the difference between those is delta phi ms. So we can write this. The energy would be minus E delta phi by ms. So if we want to get this purple arrow, that's the difference between E psi s and the Fermi level of the metal, which will determine the total electrode potential. Then you can see that the total electrode potential, this E, is the electrode potential. So we started with how to define the electrode potential, and now know that the electrode potential is nothing but the work function of a metal electrode inside an electrolyte with respect to vacuum, right? So the metal is immersed in the solvent. So it is not just work function of the metal itself. We have to consider the solvent also, right? Divided by E, so that you get the potential. This is sort of energy. So you divide it by the charge. Now, if you look at this, let's leave the denominator here and look at this factor, that is this entire arrow here. You can see that I can get that by adding mu em, right, plus this minus E delta phi m by s. That is the difference between the surface potentials of the metal and the solute. That is the inner potential, or the Galvani potential, which we derived, right? So then this minus the last part, this part is simply minus E chi, right? Minus E chi S by V, right? So or that would be equal to essentially minus mu em by s plus E delta phi ms by E, plus minus into minus would give us another plus E chi S by V by E. So these E's cancel out. So ultimately we would have minus mu em by E plus delta phi m by s, right? Plus chi of s by v. And this makes sense because now if this would be what it would be just for the metal, right? But this metal is immersed in a solvent, and for an electron to go from the solvent, from the surface of the solvent to the metal, there is an energy gap of E delta phi, right? So this is sort of the activation energy. It has to have that. So that's the extra term here. And then on top of that, this reaches the surface. So if it goes from here, this is just the metal, right? From the Fermi level of the metal to here is within the metal. But from here to there, it is in the solvent, and from here, the solvent surface to the vacuum. So that's what these two terms are, right? So in other words, we can write electrode potential E as minus mu E metal divided by E plus delta phi m by s. This is the inner potential difference, right? Plus chi of s by v. This is the solvent in vacuum, the electrolyte in vacuum. This is the surface energy of the solvent in vacuum. So this is what corresponds to the absolute electrode potential. So in a battery, when we have two electrodes, the net voltage that we are getting is the difference between these two electrode potentials. Now notice here one thing, that this is only a function of electrolyte. It depends only on the electrolyte you choose, because this is the surface energy. So if I have the electrolyte and this is the outer potential, this term is just at the surface of the electrolyte. So this is just a function of electrolyte, in the sense it depends upon the electrolyte that I choose, and this depends upon the metal I choose, right? So the first and last terms, this depends upon the metal, and this depends upon the electrolyte, whereas this delta phi ms depends upon the interface, right? So this is where our SEI layer, the solid electrolyte interface comes into picture. Now, so far we have considered, metal electrodes. But if we consider a battery system like SPAN or sulfur electrode or any cathode like LFP or LCO or LTO or even graphite, these are not really metallic. Graphite is semi-metallic, and other electrodes are not conducting. So this mu E is not going to stay pinned. The reason is because if you take a system, right? If you take a system, for example, let's say if you take, let's say, a metal electrode, and let's say this is a semiconducting electrode. Let's say we connect these two through a battery so that we can take some electrons from here and electrons from the metal and put them on the semiconducting electrode. So in case of the semiconducting electrode, the problem is that you usually have the conduction band and the valence band and no states in between. No density of states in between this. Right. So now in case of if you treat this as a simple capacitor, right? Let's say we move n electrons from metal to the semiconductor, then this changes the potential of the semiconductor, delta V, as Q by C geometric capacitance of the semiconducting electrode, right? And this is accompanied by a change in the chemical potential of the semiconductor, right? Which is equal to n divided by the density of states at the Fermi level. So this is the density of states at the Fermi level. In case of a metal, the density of states at the Fermi level is very high for metal. So delta mu is almost zero, right? So that's why in the previous expression we have only mu em. But now if we have a semiconducting electrode or an insulating electrode like sulfur or SPAN, then this delta mu is no more zero because the density of states at the Fermi level is not high enough. You may have a conducting path, you may have added conducting additives, so you have a conduction path, you have a percolating path, but that doesn't change the nature of the SPAN material or that of sulfur. Right. So there is going to be, if you put charge into the SPAN electrode, it is going to be accompanied by a chemical potential change as well. In the case of metal electrode, whatever we have derived thus far, we have ignored this because in case of a metal, the density of states is very high. So delta mu is almost zero. But what if this density of states is not very high? Then delta mu is not zero. It is some non-negligible term. So then the electrode potential in case of a very simple first order approximation for a non-metallic electrode would be minus mu e of the semiconducting electrode plus delta mu, right, divided by E plus delta phi ms or SE, semiconducting S, plus chi of S by V. The only thing we added was this delta mu term, right? So then this is going to be delta mu is going to be the number of electrons moved by density of states of EF, right? So this would be the total charge divided by the charge of each electron. That's what will give you N, right? And then you have DOS at EF. And now if you look at this if you look at this, look at just this part, you would see that this E DOS EF, if I have a denominator E here, so if I divide by E, I would get E squared. So I would get E squared by DOS times EF. This is what we call as the quantum capacitance, right? So then this term has to be included in that, right? So delta mu by E basically gives Q by C quantum capacitance, right? So this depends upon the total charge that is being transferred. So now our electrode potential is no more constant. It is going to be shifted by an amount of Q by C quantum by E plus delta phi SC by S plus chi of S by V. So this shift, this extra shift that happens due to the limitation of quantum capacitance or limited density of states leads to polarization. This is what we started with. Recall that electrochemical polarization does not mean the same thing as what we mean in physics. In physics, we often use the word polarization to indicate dipole polarization. Here it is not dipole polarization, it is rather the shift in electrode potential, right? And so if you want to reduce this polarization effect, then you ought to increase quantum capacitance. So if you increase the quantum capacitance, then this delta mu term would be gone, or it would be reduced, so that you would not have much polarization. And this polarization could be looked at as, you could have voltage versus capacity, right? So you would have a charge discharge curve that looks like that, and this difference tells us about the polarization, or this polarization is directly giving us delta mu by E, or it is giving us the total charge by quantum capacitance, right? So in case of span, because of the presence of nitrogen, density of states at the Fermi level might be higher, so the polarization effects may be weaker, right? So that's how quantum capacitance plays a role in polarization. We are going to look at how this quantum capacitance also affects the total charge capacity in the next lecture.